Hi, everybody. So, in today's task, which is task 1.10, which is the 10th task of Module 1 from Math 1, we are going to be working on 3 learning targets. Now, this is going to be all about looking at an equation and making some decisions about what we know about a sequence. Up until now, we've always been given a sequence or a different representation, and we've been creating these equations. Now we're going to use what we know about creating the equation to analyze the sequence. So here are our targets. I can identify if a sequence is arithmetic or geometric and support my reasoning. So how do you know that it's arithmetic or geometric if all you've got is the equation? I can identify if an equation is explicit or recursive and support my reasoning, including its efficiency of use, which means which equation would you choose if you had to pick one to use it to find one of the terms. So is it is it explicit or is it recursive? And which one would you choose for this problem? And finally, I can identify the common difference or common ratio in an arithmetic or geometric sequence and interpret it in the context of a problem. This is something we've done before where we've explained what that common difference or common ratio means. All we're going to be doing now is starting with an equation, whereas in the past we started with a story problem or we maybe started with a table of values or something. So let's get into it. How much information do we know about a function given only an equation? Let's see what we know so far. So here's the equation that we have. G of x is equal to g of x minus 1 times 3, and g of 0 is equal to 4. So the first thing I would decide here is this arithmetic or geometric? Now, when I'm looking at this equation, I know that when I'm looking for whether it's arithmetic or geometric, I need to think about the type of pattern that I see. This multiplying by 3 here tells me that the pattern is multiply by 3. Over and over and over again. Based on that information, I would say that this is a geometric sequence because the pattern is multiplying by 3 each time. And again, those words each time are really important because it means we're doing it over and over again. Now, since we're multiplying, that tells me that I have a common ratio. Now, a common ratio is because we're multiplying, and the value would be 3. If our pattern was adding or subtracting, we would say that we have a common difference. And then last but not least, based on the format of this equation, because I'm seeing I have g of x, which is the output, is equal to g of x minus 1, which is the output, I'm going to say that this is a recursive equation. How do I know? Because the equation uses the previous term. Now, remember when we talked about writing recursive equations, we said g of x is the current term and g of x minus 1 is the previous term. So because the equation uses the previous term, then we must have a recursive equation. Now, an explicit equation doesn't use the previous term. It just uses any input you want. Doesn't matter what the previous term was. So that's kind of the big difference between these two types of equations. Now, the next equation we're given is f of n is equal to negative 5 parentheses n minus 1 plus 2. A couple things here. One of the things I want you to realize is that when we write equations, we actually often write these equations slightly differently. We usually write these equations as we start with the 2, and then we have minus 5 parentheses n minus 1. So we usually kind of flip-flop these two things, but you can write it either way. It doesn't matter. If it's helpful for you to just sort of flip-flop the equation, so if you think about it, it's kind of like spinning it around. If it's helpful for you to do that to see the pattern better, you certainly can. Is this arithmetic or geometric? Well, the first thing I'm noticing is that it doesn't have a multiplication pattern with a recursive like this one does. It's not a recursive equation, it's explicit because there's no previous term. So if an explicit equation, well, let's start with that then, since that's the first thing I noticed. It is an explicit equation because it does not use the previous term. So if this one is an explicit equation because it does use the previous term, this is not, if this one's a recursive equation because it does use the previous term, then this one is an explicit equation because it does not use the previous term. Now, given that information, I'm going to look at what kind of pattern I see here. Because this n minus 1 is not an exponent, that tells me that this is an arithmetic sequence. And the reason is because the equation does not have an exponent. All explicit geometric sequences are going to have exponents in their equations. That means that there's automatically going to be a common difference. And we're going to find the common difference by looking at what number is multiplied by the variable. So because the -5 is multiplied by the variable, and it doesn't matter which order you write the equation, it's the -5 is multiplied by the parentheses, the variable, then the -5 is going to be my common difference. If I'm given this type of equation, the first thing I notice is that I do have an exponent this time. And as soon as you see an exponent, it tells you that this is a geometric sequence because the equation uses an exponent. Now, common difference or common ratio. Because it's geometric, we're going to have a common ratio, and the common ratio is always the base of the exponent. So in this case, it's 1/3. Recursive or explicit. Because this equation does not use the previous term, so it doesn't say h of x is equal to h of x minus 1, it just says start with 9 and multiply by 1/3. This is going to be an explicit equation because the equation does not use the previous term. Now, by contrast, if I look at the next example, I can see right away that this equation is using the previous term. This output is the previous output minus 2. So right away I can say that this is recursive because the equation uses the previous term. Another thing I'm noticing is that the pattern at the end here says minus 2. So because the pattern says minus 2, it tells me that this is an arithmetic sequence because the pattern is subtracting 2 each time. Now that also tells me that I have a common difference because as soon as I know that it's arithmetic, I know that there's a common difference. In this case, it would be minus 2. For the next equation, we have f of x is equal to 2/5 x plus 8. Now, right away, I can tell that this is an explicit equation, and I can tell that this is explicit because the equation does not use the previous term. Now, based on this equation, because there's no exponent, I'm going to say that it's arithmetic. As soon as I know that the equation is arithmetic, I know that it has a common difference. And the common difference is always the number attached to the variable, whether it's at the beginning or the end of the equation. So in this case, that would be 2/5. In the next example, we have b of n is equal to 2/5 8 to the nth power. Right away, because of that power, I'm going to say that this is a geometric equation because the equation uses an exponent. Now that means it's going to have a common ratio, and the common ratio is going to be the number I multiply by over and over again, which in this case is the base of the exponent, which is 8. Since this equation does not say b of n is equal to b of n minus 1, so it doesn't use the previous term, I'm going to say that this is an explicit equation because the equation does not use the previous term. Now, in addition to being able to really know a lot about a pattern based on an equation, we need to be able to know a lot about a pattern based on a scenario. So let's see what we know so far. Yusuf wants to become stronger. On the first day, he lifts 1 pound weights. On the second day, he lifts 2 pound weights. And on the third day, he lifts 4 pound weights. On the fifth day, he lifts 16 pound weights. Is there a common difference or a common ratio here? And we should explain the meaning in the context of the scenario. Just like in our previous examples, I would highly recommend making a table of values here before you make any decisions. So I'm going to have x and I'm going to have f of x. Now it tells me in the problem that on the first day, he lifts 1 pound weights. Second day, he lifts 2 pound weights. Third day, he lifts 4 pound weights. We don't know the fourth day, but then on the fifth day, he lifts 16 pound weights. Now, based on this story, I'm going to see that the pattern is that we are multiplying by 2 each time. So if we have a multiplication pattern, it tells me that this is a geometric sequence. With a common ratio of 2. Now, what does that mean in the context of the problem? Well, in the context of the problem, what this means is that the amount of weight that he lifts doubles each day. So we need to just say that. So we're going to say that the amount of weight, so what are we measuring? The amount of weight he lifts doubles, so that's the pattern. And how often does it double? Each day. So what are we measuring? What's happening to it? And how often is it happening? Manny wants to spend his money wisely this summer. So he starts off with $1,000, and after the first week, he still has $950. After the second week, he has $900, and so on. Again, I would recommend making a table of values. So we've got the weeks, we've got his amount of money. He starts off with $1,000, so no time has passed, he has $1,000. After the first week, he has $950. After the second week, he has $900, and so on. Now, based on this pattern, we are subtracting 50 each time, which tells me that this is an arithmetic sequence. So there's a common difference, and the value is minus 50. Now, to explain the meaning, let's start with what are we measuring? We're measuring the amount of money he has left. And what's happening to it? It decreases by 50. $50. How often? Each week. So just as a reminder, a refresher before we go to the next page, what are you measuring? How is it changing? And how often is that change happening? All right, now this is where it's going to be a little different than what we did before. If we have a scenario and an equation, we're still going to need to be able to pick out the common difference or the common ratio and explain what it means in the context of the problem. So it says here, your parent planted a small tree in your yard. The following equation represents the height of the small tree each month. It says T of n is equal to 3 plus 2n. Now, this equation does not have an exponent. So based on that information, I'm going to say that this is an arithmetic sequence. If this sequence is arithmetic, it's going to have a common difference. And the common difference is always going to be the number attached to the variable, which in this case is 2. So my value here is going to be 2. Now that means that whatever we're measuring is going up by 2 each time. So what are we measuring? We're measuring the height of the small tree. So we would say the height of the tree. And what's happening to it? It's increasing. Oops, I'm using the wrong color. Increases by 2. How often? Each month. A ball is dropped from the 8th floor window. The following equation represents the height of the ball in feet for each bounce. Now, based on this equation where I see an exponent, I know that this is a geometric sequence. So because this is geometric, I can tell that it's going to have a common ratio. And the common ratio is, again, always the number attached to the exponent, which is the variable. So the variable tells you where to look to find the pattern. And that's going to be 1/2. So what are we measuring? We're measuring the height of the ball. Now, having a common ratio of 1/2 means that it is cut in half. So the height of the ball is halved or is cut in half. And then how often? Each bounce. Now, the last thing we're going to talk about today is, if we know a lot about different types of equations, do we know which equation is more efficient? More efficient means faster or better to use at different times. So let's consider the following situation. If you are asked to find term number 37, so the 37th term in a sequence, you know the first term. Would it be faster to find term number 37 using explicit or recursive? Well, let's think about the options here. For explicit, we can find any term. But for recursive, we can only find the next term. Now, we know term number 1, and we want to find term 37. Since term 37 is not the next term, using the recursive formula would be really hard because we would have to find term number 2, 3, 4, 5, 6, 7, etc., all the way up to 37 before we could know that one. Since we don't know 36, which is the one right before 37, using the recursive formula is going to be very inefficient. So in this case, I would say that I want to use the explicit formula. Now, the reason is because we do not know term 36, which is the previous term. So the explicit formula would be more efficient. Now, that doesn't mean you couldn't use the recursive. It would just be less efficient, which means it might take you longer than just plugging the number 37 into the explicit equation. If, for example, you are asked to find the 37th term and you know the 36th term, would it be faster to use explicit or recursive? Now, in this case, our situation has changed. You know the 36th term. You want to know 37. Because you know the number that comes right before the one you're interested in, using the recursive would be more efficient. And the reason is because you know the previous term, which is term number 36. If you are asked to find the 37th term and you know term number 30, would it be faster to use explicit or recursive? This is a situation where I think because 30 is relatively close to 37, you could probably make an argument that using the recursive would not take very long. But I still think that because you don't know the previous term, you would want to use the explicit because you don't know the previous term, which we need in order to use the recursive formula. So since we don't know it, we would want to use explicit. All right, thank you guys so much for watching. I appreciate that you're taking notes and paying attention, and I hope I can see you again soon.